Well, what is that chemical potential that's going to help us determine whether something is spontaneous or not? Could enthalpy be that chemical potential? So remember enthalpy from Chem 1A? So delta H is equal to heat at constant pressure. So enthalpy predicts that all exothermic reactions are spontaneous and all endothermic reactions are not spontaneous. Is that true? No, it's not. Some endothermic reactions are spontaneous. And some exothermic reactions are not spontaneous. So enthalpy is not the thing that's going to predict whether this is spontaneous or not. So here's an example of a process that is spontaneous but has an increase in enthalpy. So if we melt ice, so here we have an ice cube on a surface and it's melting, and this is above the freezing point of water, right? So ice melting, is that exothermic or endothermic? How do you get ice to melt? Do you put heat into it or take heat out of it? Make it hotter or colder? Hotter. So heating the ice is going to make it melt faster, and so that's how we can reason out that this is an endothermic process. So as the ice melts, it's absorbing heat, it's increasing in entropy. So, the enthalpy is increasing. This says entropy. I'm not sure. Man, I'm finding typos today. I'm not sure that one's supposed to be there. Anyway, so that doesn't seem like it should happen, right? Because it's an endothermic process. You have to put heat into it. So why is it happening spontaneously? Dissolving sodium chloride in water. Evaporation of liquid water to gaseous water. What do these have in common? They involve an increase in enthalpy. So see, this is the one I wish hadn't recorded, because this is not going well. These two do increase in enthalpy, but the more important thing is they have an increase in entropy. So that word is supposed to be there. Yeah, I'm just going to be deleting this one. It's bad. So the chemical potential that helps predict spontaneity is entropy. So in each of these processes, water evaporating, ice melting, sodium chloride dissolving, we have an increase in entropy, an increase in disorder or randomness. So water in the liquid state evaporating. Here, these guys are really close together. Here, they're very far apart. Sodium chloride dissolving. Here we have a nice crystal, very organized. And then when it dissolves, these guys can all separate and go their own way. Back to the ice cube that I misinterpreted. Here we have solid water with our water molecules all lined up and fixed in position. When we melt it, now they can swim around. It's an increase in entropy or disorder. And so that's what we informally think of it as, disorder or randomness. Okay? It's sort of kind of becoming fall here in the middle of October. And pretty soon, give it a few weeks, the trees are going to start turning colors and their leaves are going to fall. When the leaves are on the tree, they're in a kind of order, right? Each branch has so many leaves and they're separated by this distance, and there's like two opposite, or they're alternating depending on the plant, right? And they're all on the tree. When those leaves fall off, do they fall into neat little piles? No, they go all over the place, right? 52 card pickup, right? You play that? Deck of cards and you just throw it all over the place. Becomes more disordered, right? Increase in entropy. Children's rooms. You can go in there on Saturday and help them get everything perfectly organized and clean. And by Sunday night, what does it look like? Looks like a bomb went off. What happened? This is entropy. So, why bother is sometimes where you get to. So, entropy is given the symbol capital S. Don't ask me why. No idea. This is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. Well, that's nice. I'm pretty sure that didn't mean anything to anybody. We will explain. So entropy is equal to a constant times the natural log of W. K is called the Boltzmann constant. There's its value. We're not going to use that. W is the number of energetically equivalent ways you can arrange the components. The units of entropy are joules per Kelvin, which, are just really coming from that Boltzmann's constant. Okay, so let's try to think about this. Imagine a fixed amount of an ideal gas, constant pressure, volume, and temperature. So the state of this system is defined by the pressure, the volume, and the temperature. That can also be referred to as a macro state. So the energy of the system is going to be constant as long as we keep pressure, volume, and temperature the same. But where the energy is anything but constant. Each molecule or atom in that gas has kinetic energy. It's moving. And so where those particles are, where the energy is, can change, and it does change. So at any one instant, a particular molecule could have high kinetic energy, or it could collide with something and lose kinetic energy and have low kinetic energy. So not only is the kinetic energy moving around in the container as the molecules move, but we also have them gaining and losing energy to each other. A lot of stuff going on. So a microstate is the exact internal energy distribution among the particles at any one given instant. So it's like a snapshot. Where are things now? Particles A, B, C. What are your energies? Where are you? And, it's not going to stay that way. So a given macrostate exists as a result of a number of different microstates. So the macrostate remains constant while the microstates change as the energy of the system constantly redistributing itself among the particles of the system. So we can think of W as the number of possible microstates. And it's probably still not making much sense. Okay, so here we're going to look at two systems, System A and System B. Each of them has two particles. Total energy of each system is 4 joules. In System A, there is only one possible energy that the particles can have. They're both 2 joules of energy, right? So is there any other way to arrange this energy? No, there isn't. System B, we could have energy of 1 joule or 3 joules. So to have 4 joules, we're going to have one down here and one up there. But why is the blue one down there? Why isn't the blue one up there and the red one down there? Well, that could also be possible. So here we have the blue one with the higher energy and the red one with the lower energy. These are equivalent in energy, right? The total energy is the same, but it has 2 different microstates, and so it has greater entropy. So this is one we do want to try to get our brains around. System A, Same amount of energy as system B, total of 4 joules. But here, there's only one option, and so both of the particles are in the same option. Here, there are 2 different possible levels. And so we can put the red one high and the blue one low, or the blue one high and the red one low. And in terms of the macro state, that's the same because we don't see how it's distributed, but there's actually 2 different microstates. Questions? So the entropy of a state increases with the number of energetically equivalent ways to arrange the components to achieve that particular state. The state with the highest entropy also has the greatest dispersal of energy. So in energy B, the energy is dispersed over 2 energy levels. So the energy is dispersed over 2 levels. Here, it's only in 1 level. So this is spread out. State in which a given amount of energy is more highly dispersed or more highly randomized has more entropy than a state in which the same energy is more highly concentrated. So the second law of thermodynamics says that for any spontaneous process, the entropy of the universe increases. That is not the entropy of the system, it's the entropy of the universe. So that's the criteria for spontaneity. Entropy is a state function. Remember what that is? The illustration in Chem 1A was a mountain, climbing up the mountain, and your change in elevation is a state function. It doesn't matter how you got up the mountain. If you took the long curvy path, you went straight up, or my preference, take a helicopter, right? Your change in elevation is the same. The distance you traveled is different. But a state function doesn't matter how you got there, it's just where you started and where you end up. So entropy is a state function. It just depends on the final entropy and the initial entropy, and we don't care what happens in between. That makes things much easier. So here we have an ideal gas in this interesting little contraption here. So here we have 4 particles of this gas, and on this side there are no gas particles. So that's a vacuum. So if we open this stopcock, this gas is going to move over here. The pressure at which it expands is 0. It's not pushing against a pressure. The volume is not increasing against a pressure. It's just increasing. So there's no work. The work is 0. So the total energy of the system doesn't change, but the entropy does, because now these particles can be in different places. So we can have different possible states that are equivalent in energy. We can have our original state, where all the gas particles were on the left. We can have state B, all the particles on the right. Same amount of energy. Or we can have state C, where we have 2 on one side and 2 on the other. Or we could have 1 and 3 and 3 and 1, right? So we have multiple microstates possible for each macrostate. We're only going to look at these 3. There's more. Yeah, I said that wrong again. So these are our 3 different states. They all have the same energy. But there are, each of these has a different possibility for microstates. So let's look at that first one where we have all the particles on the left. Those atoms are identical, but let's just call them 1, 2, 3, and 4. In state A, there's only one possible microstate. All of those particles are on the left side. In state B, all the particles are on the right side. That means everybody's on the right. There's only one microstate. Whereas state C, where we have 2 on each side, there are 6 microstates. We could have 1 and 2 on this side and 3 and 4 on that side. We could have 2 and 3 and 1 and 4. 1 and 3, 2 and 4, 2 and 4, 1 and 3, 1 and 4, 2 and 3, 3 and 4, 1 and 2. Right? Different ways to arrange these things. The overall energy of these is the same. And when we just look at them, they look the same as this, but these are different particles, and so being in different places is a different microstate. So because of these microstates, the probability of finding atoms in state C is 6 times greater than state A or state B, because more microstates, higher entropy, and that's going to be favored. If you increase the number of atoms to 20, now instead of 6 microstates, you get 184,756 microstates for state C, which is just equal on each side. Whereas the microstates for states A and B, all atoms on one side or the other, remains 1. So a change in entropy from state A to state C is positive because the final entropy is larger than the initial entropy. Do you have a picture? No. Let's go back to this one. So if this state becomes that state, 2 of the particles move over. This has 6 different microstates. This only has 1. Number of microstates is related to the entropy, higher entropy. So by going from state A to state C, the entropy has increased. So that's going to be a spontaneous process. You can also think of it this way. When the atoms are confined to one flask, their energy is also confined. When they're distributed, now their energy is spread out over a greater volume. Energy is dispersed. So energy is kind of like those playing cards. You know, when you've got them all in a deck, it's very confined. And when you throw them or do anything to them, what happens? They're going to spread out. The energy spreads out, and that's what's favorable. Questions? This is such a Monday lecture. Sorry. So the second law of thermodynamics explains things that are not explained by the first law. So in ice water, we get heat traveling from the water to the ice. It doesn't go the other way, right? The water has higher kinetic energy than the ice does. And so the heat is going to move from the water to the ice. The first law does not prohibit the ice from getting colder and the water from getting warmer. It just says that energy has to be conserved, right? But we know that what happens is the water is warmer, and so the heat goes to the ice, it goes to the colder thing. The heat then is getting spread out. It's not becoming more concentrated. Second law says that energy is dispersed, not concentrated. If the opposite happened and the ice became colder and the water became warmer, which, you know, you're like, well, that couldn't happen. No, it couldn't happen. It just doesn't happen. It doesn't happen. Because that would involve concentrating the energy, decreasing the entropy. Oh, thank goodness.